Wilf Pinfold. Thank you for joining us today for this ACM Special Interest Group for High Performance Computing webinar. With over 1,000 members worldwide, SIGHPC is a volunteer-led organization dedicated to improving careers and highlighting the impact that HPC has on our everyday lives. To join or learn more, check out www.sighpc.org. Today's topic falls into the category of highlighting the impact that HPC has on our everyday lives. Over the last 3 decades, HPC has become increasingly important in manufacturing, weather forecasting, medicine, entertainment, and many other aspects of daily life. You would be hard-pressed to experience a normal day for an average citizen without encountering something that wasn't impacted by HPC. ACM, SIGHPC, and the SC Conference have launched a program called HPC Matters to highlight this impact. I encourage you to look for the short videos that have been produced for this program and posted at sc15.supercomputing.org/media/video-gallery. Today's webinar will discuss the use of high-performance computing in the design of aircraft jet engines and the gas turbines used to generate electrical power. It is my honor to introduce Dr. Brian E. Mitchell, a Senior Principal Engineer at GE Global Research with technical leadership responsibilities in the Aerospace Systems Organization. Brian is responsible for the development of GE's in-house computational fluid dynamics software used at GE in the design of turbomachinery aerofoils. His technical interests include aeromechanics, turbomachinery aerodynamics, parallel scalability, and code performance. Brian holds a PhD in mechanical engineering from Stanford University and has been with GE for nearly 20 years. Ladies and gentlemen, Dr. Brian Mitchell.
Thank you, Wilf, for the kind introduction, and also thank you for the invitation to speak today. So as Wilf highlighted, I'll be talking about the way we use high-performance computing in our design of our aircraft engines. I'll be showing some examples about how the HPC and modeling and simulation drive design. I'll be talking about the way competitive pressures are ratcheting up the things we need to do, and then the pressures on design and high-performance computing. I'll be talking some about the elements of how a successful strategy to implement and deploy high-performance computing in an industrial environment. And I'll be closing with some thoughts about the direction of software and high-performance software and its response to high-performance computing. As we get started, at GE, we're in a part of our yearly cycle. We're in the throes of advocating for funding for the following year. And I was reminded of a dialogue I'd had a couple years back with a senior manager as we were laying out how to advocate for high-performance computing. And we were working our way through how does one justify the return on investment that the high-performance computing and modeling and simulation provide. And we were really struggling with it because you start asking questions about, what's it going to cost you? You can really easily lay out it's going to cost so much money in the following year, or you've spent so much money to create this set of capital equipment in terms of computers and whatnot. But when you start trying to wrestle with the return on investment, it gets hard because you're really recognizing that everything you're doing is part of everything. It's a key enabler for so many designs across so many different parts of the enterprise. And this gentleman finally said, it's kind of like asking what's the return on investment or the value story for electricity. In a sense, the value of electricity is all Western civilization. Now, I wouldn't want to say HPC is quite the same level of impact, but the comment really spoke for just how integral HPC and modeling simulation is to our fundamental engineering processes here at the company. It really is just part of how we do our daily work. So I just share that up front that what I'll be talking about today is really integral to everything we do at GE when it comes to design of jet engines and cousin technologies. I wanted to highlight on this slide that GE is actually a fairly old company. It goes back to 1892. And I bring this up because a core business for GE from the beginning straight through to now has been around the generation of electrical power. And electrical power certainly has evolved over time in terms of the way you go about it, and certainly the efficiencies involved have improved. But at its core, most power comes from involves rotational turbomachinery, whether that's in the form of steam turbine generating power, or a gas turbine steam turbine combined cycle, or a nuclear power plant driving a steam turbine, or a wind turbine. This is a core technology that GE has been using and developing and selling for nearly 120 years. Jet engines, which I'll use as the focus of my remarks, is a business that GE has been in since the late 40s. And it really is the same technology as used for electricity. It's just a rotational turbo machine which is used to generate thrust to drive an aircraft forward. A core business that we've been at for a long time. However, the way we have approached the design challenge has changed radically. That's the part of the story I'll be sharing today in terms of the use of high-performance computing. As I said, I'll be focusing remarks on aviation, but GE is a broad company, and what I'm talking about today impacts our power and water business in terms of steam turbines and gas turbines, our oil and gas business where we make process compressors, and then aviation. The point of this is that turbomachinery continues to be a core business for GE, and a large fraction of our revenue come from this technology. I happen to sit as part of the GE Global Research Center in upstate New York. You can see a picture of our campus there. And as I go forward, I'll be talking a little bit about the role that groups in the businesses play in the high-performance computing relative to groups in the research center play in high-performance computing. They're each part of the whole picture that allows HPC to impact the design of jet engines. As we talk about jet engines, you have to appreciate that what drives design is really what the market is demanding in terms of our need to deliver improved products. Aviation is at a very interesting space right now where the majority of the aircraft engines flying are being changed out with next generation products. And we're seeing that in the airframes as well, the aircraft delivered by the Boeings and the Airbuses. Let me talk you through aspects of the story. If you look at the upper left, I'm showing a picture of a LEAP engine. This is an engine which will be flying fairly soon on next generation Boeing 737s and Airbus A320s. This is really the most popular class of engine sold. It supports the single aisle aircraft. The engine that GE is getting ready to field will have a 15% fuel burn improvement relative to current generation technology in terms of our CFM56 engine. This is a significant fuel burn improvement, and it's directly driven by the needs of the airlines and driven as well by the competitive pressures caused by the other engine manufacturers. The GNX on the lower left is a very similar story. This is the engine that powers the Boeing 787 Dreamliner as well as the Stretch 747. It also has a 15% fuel burn reduction relative to the previous generation GE CF6 engines. Once again, a major improvement in the fuel burn, which had required a complete reworking of the engine and its architecture. The GE9X in the upper right, this is the engine which will power the next generation Boeing 777s. It shows a 10% fuel burn reduction over to current generation GE90. And if you're wondering why 10% versus 15%, it just reflects that the GE90 is a newer engine that we're replacing, so it's longer, not as much time in between. But once again, a major improvement in fuel burn requiring advances in the cycles and the individual component efficiencies. And then lastly, in the lower right, the Passport engine. This is an engine which will support the general business and general aviation space. I don't have a number here because we don't have a previous GE offering here, but in terms of the state of the art, once again, it's a 10 to 15% fuel burn over what was available preceding this. If you consider that GE products, be they jet engines, gas turbines, or locomotives, burn roughly $1 billion of fuel every year, you can appreciate not only the true business impact of improving our products and ensuring we maintain market share, but you also can appreciate the environmental impacts in terms of reduced emission, reduced carbon content, and the like. So big deal here in terms of products which are radically better than previous generations. All of it goes back to the forces in the market in terms of competitive pressures that roll up to the design teams. So why do we care about high-performance computing? It's really because we care deeply about the use of modeling and simulation as part of design. And when we talk about high-performance computing and the use of larger computers, what particularly drives this is the discipline of computational fluid dynamics, otherwise known as CFD. And at the GEs, we look at the design of these turbomachinery parts, jet engines, gas turbines, and the like. CFD is critical to all of our turbomachinery product lines. And so it's how we will design for aerodynamic efficiency in a compressor. It's how we worry about efficiency and noise from a fan blade. It's how we design for the heat release that a combustor has to provide. It's how we deliver the turbine efficiency as well as worry about the lifespan of a turbine part. It's also how we will worry about noise and design for noise out of the jet exhaust out the back of the engine. So it impacts aerodynamics, aeroacoustics, heat transfer, and combustion for all of our product lines. And this is not a new thing. We've been working in the space of computational fluid dynamics for the design of these parts for something like 40 years. And while it's been around for a while, it has changed constantly in terms of the level of fidelity that can be delivered, the amount of penetration into the design process, and the overall impact it has had on the way we do design. So just to give you an example of how modeling and simulation is used, what I'm showing here on the left is a compressor stator vane from a previous generation design. It had presumably been designed with whatever was state of the art at the time for computational methods. But when it was reanalyzed some years later with more advanced modeling simulation, what we could see quite clearly is that we had a pocket of reverse flow up in that outer diameter. And I'm marking here in blue the flow that's going from front to back, the correct direction, and in the red is the flow that's reversed and it's going opposite or from back to front of the engine. And this red flow represents high loss. It's really air that's doing the wrong thing. It means the part is not achieving its mission because part of the flow volume is doing the wrong thing. And I think it's probably a good adage that if a designer is able to simulate a physical effect and have some way to visualize that physical effect, designers are very clever people and they're able to find creative ways to modify the blade shapes, modify the geometry to improve a part so it can achieve its mission. And in this particular case, the designer added some extra three-dimensionality to the shape by bowing the blade. And if you look left to right, you can see some of the subtle changes in terms of the way the blade bows in the rotational direction. By doing that, you change the loading of the blade up in the outer diameter, and that's sufficient to take out this pocket of reverse flow. And now you'll see all the flows marked in blue, representing the fact that it's going from front to back the correct direction. And now we have a much higher performing part as a result. So that's the sort of thing that designers do day in, day out to use modeling simulation to start with a baseline design and incrementally and deliberately improve it for efficiency, for life, and for other aspects of performance. Now, as I said, we've been doing this for 40 years, but it's not a stationary field. As our products have improved and as we're increasingly asked to push the state of the art to deliver better fuel burn or quieter engines, to deliver more electricity output from a gas turbine, we're finding that we're pushing our design knowledge, we're pushing ourselves into different parts of the design space, and increasingly that means that the level of sophistication required in our modeling simulation increases as well. And that result is we find we need more computational horsepower to accomplish our mission. So if you look at this top row, this is an example of how we're seeing changes in our way we design a low-pressure turbine. The leftmost image reflects a steady multi-stage calculation of a low-pressure turbine. Now, the geometry is unsteady. We have rotating stationary blades interspersed in the turbine. So when you run a steady analysis, you're introducing some implicit assumptions about physics, which you then have to model. And what we're finding is in order to do a better job for modern engines, in order to expand the design space to worry about things like airfoil clocking, we're moving to unsteady analyses of the same component. That move from steady to unsteady is a roughly 1,000-fold increase in the number of floating point operations required to run the simulation. So it's a big deal. In the middle row, this is an example from jet exhaust. What's interesting about this example is that if you ask what kind of CFD could you perform, say, 5 or 10 years back, it would be some sort of steady RANS calculation. And the reality is that calculation wasn't worth squat. Its fidelity, its ability to match data wasn't accurate enough to be used as part of the design process. And so all we could do was run testing of those components. Now, testing has its own problems in terms of accuracy, but more importantly, it has very slow turnaround times. So you really can't do a very good parametric investigation of your design space. Well, fast forward to maybe 2008, 2009, we could start running large eddy simulations. So these are calculations where we're now including a large portion of the turbulence field by first principles. And with these sort of calculations, we could start predicting the noise and validate against data. And this now drives our design process. And so it ends up being faster turnaround time and cheaper than the previous way of using only experiments. The bottom example talks about how we look at our fan designs. In the past, all we could do for a fan blade is look at a single fan blade, steady flow, and design for the desired operating points. Increasingly today, we'll worry about the fan in the environment of the full inlet configuration. This requires us to run unsteady fan, the full row, so not one fan blade, but maybe 20 or 22 fan blades, part of the outlet guide vanes, and then we'll include part of the nacelle all the way around as well. This sort of calculation is 10,000 times more expensive than what we would have only looked at a few years back in terms of the isolated fan blade. So as we're pushing the state of the art, as we're driving to increase fuel burn, our calculations, the fidelity is going up, and this is pushing our reliance on high-performance computing and our need for ever larger computers. So let's shift gears a little bit. Let's talk about how do we utilize this high-performance computing. I've talked about why it's required and why it's becoming even more important. Let's talk about how we utilize it, and also let's start talking about how we deploy it at the scales we're talking about. So when we think about using increased horsepower, we think about this in terms of three broad vectors. First, we can imagine if you had a bigger computer and more sophisticated algorithms, you could use that as a microscope. So you could dial up the physics. So as a for instance, you could look at a low pressure turbine, and instead of running a steady simulation, perhaps you run an unsteady simulation. Instead of running a RANS calculation, which models a lot of the turbulence, perhaps instead you'll run a LES calculation to capture more of that turbulence by first principles. That's an example of using the computers that you've purchased as a microscope. Another way to look at this is a macroscope. So this would entail taking increased computer horsepower and broadening your field of view. So showing here an example of an open rotor. In the past, we would have only looked at a single fan blade. In this example, we're looking at the entire stage of the fan, as well as the engine housing, the pylon back to the fuselage, and that structure going across the upper right of that image is part of the tail of the aircraft. So it's taking more of a system view of the part, looking at the performance of the fan in the midst of the rest of the environment. If this engine configuration looks a little bit odd, that's because this is a possibility for what engines in the 2025 timeframe might look like. And so we're worrying ahead about the engines of tomorrow. And then third, we talk about optimization. So if you have more computer horsepower, more sophisticated algorithms, you can then look at a variety of alternative designs. And so so we'll use this to do a more thorough exploration of the design space, perhaps using a design of experiments approach, or alternatively do some sort of optimization process where we'll form gradients and move our way through the design space. The other way this gets utilized is to look at more operating points. At bare minimum, a jet engine has to be designed considering the cruise point where you're worried about the max efficiency, but you got to be able to have max power at takeoff, and you want to make sure you're doing something smart as you come into a landing configuration. So by having more computers, you can do a more robust design that takes into account all the operating points that the engine needs to operate at. So as we've evolved over time and these computers have gotten larger, we've had to get more sophisticated and holistic about the way we manage the ecosystem. And in my mind, this really comes down to four aspects that one has to manage. And I think two of these are fairly obvious, at least in terms of categories, but the other two perhaps not so much. The two obvious ones being the fact you got to invest in the hardware and you have to invest in the software. So let's take these, all four of these in order. So hardware, as a practical matter, we find we do need to own our own computers, and we have a variety of computers distributed across the world, as well as some fairly large shared facilities. But in addition to what we own in-house, we also make use of the various national resources that are available in the U.S. as well as in Europe. And let me tell you a bit of that story. As I said, we've been doing this for 40 years, but I'll pick up the story in the year 2000. This is a time frame when Linux clusters were coming into vogue in the engineering space. And back in the early days, we actually were building our own Linux clusters, much like everyone else was doing. And for the 2000 to 2008 time frame, this is what dominated our compute, is these Linux clusters, which are really great at providing the ability to run numerous small jobs. So you can imagine building enough clusters to run thousands of jobs which have anywhere from 10 to 100 cores per job. And we refer to this as capacity computing. Starting in 2008, we started looking and we started broadening our horizons and asking the question of what would happen if we could run jobs which are much larger than a couple hundred cores, thousands or tens of thousands, maybe even 100,000 cores. And instead of going off and buying an expensive computer and speculating, we reached out to the U.S. national labs as well as the PRACE program in Europe and got time on those clusters, which allowed us to explore what would it take to run a very large calculation. What are the implications for our software? What we have to do to make sure that software could run at these very large scales? And if we could run such a large calculation, what's the value story? What's the engineering benefit? What are the engineering insights that these large calculations could provide? And so we were able to do that on these leadership class computers. And what that demonstrated to us is there was a value of being able to run very large calculations as part of our design work. And so if we look at what we do today, is we still have these capacity computers, because this is an appropriate way to run the modest core count jobs, which still exist in our system. We still use the leadership class computers at national labs to run and try out very large scale calculations. But now we have something in between, which we refer to as capability computing. These are computers which are approaching the leadership class size, but not quite. And this allows us to run a small number of fairly large jobs in support of our engineering design. And this collaboration has led us not only to realize the value of capability computing, it's allowed us to try on different options for that hardware. So in our case, we now have a Cray computer, but that was not a random choice. That came out of test driving the computers we could get access to at the U.S. national labs. And it also allowed us to evolve our software to be ready for running on these computers. Second aspect of the strategy comes down to software. At GE, we use software from 4 different sources. In-house software, and I'll talk about a key in-house code before I wrap up. We make use of commercial software. In our case, that's software from the Ansys Corporation, as well as software from Cascade, at least for CFD. There's other commercial vendors for other disciplines. We make use of government software, and we also make use of academic software that's provided by our various academic and university partners. And in a moment, I have some examples, and I'll show examples of software from all of these sources. The third leg of this, which may seem a bit at odds in the HPC talk, is the need for experimental validation. The reality is that we're pushing the state of the art for modeling and simulation, and we're increasingly and constantly simulating things we have not simulated before. That fact, coupled with the fact that even with the large computers we use today, that we still don't resolve all the physics, we still don't resolve the entire engine. We have to take deliberate measures to ensure we're grounded to reality and we're not misleading ourselves. And part of the virtue of being in the business for a long time is that not only have we built up a large database of historical results we can compare our codes to, we have also built up any number of rigs, be they small benchtop rigs to lab scale rigs, as well as the ability to get data from full scale installations, be that on a flying engine or in an operating power plant or the like. So verification and validation is critically important to ground yourself as you increasingly rely on high performance computing. And then fourth is a understanding of what the roles of the various organizations need to play. So if I look here on this chart, just to highlight this, on the far left in the blue box, there's a role for research and development. This is the role people like myself play in this high performance computing picture. So these are activities such as code development, such as understanding and staying ahead of next generation high performance computing hardware. It's activities around doing an application of modeling simulation for the very first time, and thus proving out what's required and proving out the value story of doing a calculation of that sort. So, for instance, when we were first doing jobs on the national labs to prove out value, that's the sort of activity I'm referring to. And then it's also about using high performance computing to evaluate concepts, which, if successful, would be used as part of future designs. On the far right of the slide, there are a key role for the design teams. These are teams which now sit at GE Aviation, GE Power and Water, GE Oil and Gas. These are folks whose jobs are to create the metal shapes and then get those shapes manufactured, fielded, and supported. And so for them, the modeling and simulation and the high-performance computing, these are tools in their toolkit. They want to pull out the CFD, utilize it to analyze a possible design, and then go back to modifying the design in various ways. So the modeling simulation is very much a key tool in their toolkits. And in between these two groups are folks who have responsibility for deployment. And this takes a couple of different forms. One part of this is operationalizing the modeling and simulation technology that folks in the research center will create. So this is creating the automation aspects of running codes and the like. best practices for how to run codes. It's about standing up and maintaining the hardware required to run high-performance computing. It's providing the user support, whether on the compute side or on the software side. And this group also serves as a key connector between the researchers and the designers. So it's about operationalizing the modeling and simulation technology. That's the arrow from left to right on the top of the slide. And it's also about flowing back requirements for modeling and simulation from the design teams, so that when folks like myself who create software are creating software, we're doing so knowing that certain features, certain capabilities are required to support the next set of designs that our design teams will be performing. And so what I would just say here on the takeaway in the bottom is that to be successful, you need a long-term and holistic view. So this is investment across this entire ecosystem of hardware, software, validation, and ensuring you have the people and organizations are ready to go to utilize this technology. Let's talk some about some examples here. So this is looking at the jet engine. What are some of the things we've been simulating in recent years in support of our design process? So let's start at the far left at the fan. So I talked earlier how when we design fans, we increasingly have a large portion of the engine geometry as part of the fan calculation. This is an example where we've included the fan blades, the OGV, a large portion of the engine nacelle, and we're simulating this engine now very close to the ground plane. And so we're imagine this as takeoff conditions, and we've thrown a strong crosswind onto the fan. And so what happens is the flow is going from right to left, and as it goes over the engine, it separates. You got that ugly tangle of red lines on the left part of the picture are all the separated flow on the downwind side of the engine. And you're also seeing being sucked into the engine from the ground plane a nasty vortex. The reason this is important is that the inlet flow to the engine now is non-uniform, and the fan blade is going through different portions of clean and dirty flow as it goes around and rotates. This has implications on whether it's able to deliver the thrust required to keep the engine and the plane flying safely. It also has implications on whether that alternating clean and dirty flow can set up vibrations and life limit the part. These are significantly expensive calculations, unimaginable a few years back, but now being done as part of our design process. And this is, although these are still expensive calculations, it's a lot less expensive than running a full engine test out at our people site to do this experimentally. This is an example, by the way, run on in-house computers using our in-house software. If I go to the top part of the slide, I've got two examples of calculations done for a low-pressure turbine. The example on the left is a multi-stage low-pressure turbine simulation using unsteady Reynolds average Navier-Stokes, or URANs. This particular calculation was run at Oak Ridge National Lab using our in-house software. And we were trying to understand the impact of unsteady flow on the performance of the low-pressure turbine. The example on the right is a large eddy simulation of a single blade of a low-pressure turbine. This is a calculation run by one of our academic partners using a European supercomputer. And here we're trying to understand more critically how separated flow and the wake effects all interact. So we're really trying to understand more of the fundamental turbulence physics of this component. Going to the far right, this is an example of a jet noise calculation. This was run using a U.S. government-developed software package called FDL3DI. This particular calculation was run at Argonne National Labs. Earlier, when I talked about our use in the 2008 to 2011 timeframe of the national labs to prove out the value of very large calculations, this is one of the calculations we were looking at. So we ran this at Argonne National Labs, and now that we've demonstrated the value, we'll run these sort of calculations in-house in support of design. But this is a case where we're calculating the performance of the exhaust system, and more critically, calculating the noise being radiated, so we can assure the engine will be within noise regulations. And then on the lower right is an example of a high-pressure turbine calculation. This is, once again, with the in-house code on an in-house computer. What we're interested in here is understanding how the hot flow out of the combustor migrates through the high-pressure turbine. In a turbine, you have two challenges. You want to have a good aerodynamic efficiency, but you also need to be able to survive the fact that the inlet temperatures are above the metal melting temperatures of the part. And so a lot of effort goes into designing cooling strategies. And so you have to understand how the hot flow moves through the turbine and make sure your cooling is providing necessary life protection in the right parts of the engine. This is an unsteady calculation looking at the way the hot spots are migrating through, so we can ensure we have the right level of thermal life, thermal durability. And then finally, on the lower left is an example of a combustor calculation. This particular calculation was run with the ANSYS product called Fluent on an in-house computer. And it's an example of how large eddy simulations have become routine for the design of combustors. And we worry in combustors about emissions and making sure we don't pollute any more than we have to, and certainly pollute less than the regulations require. If we manage the emissions, and we also manage the dynamics, so the part will hold together and have a good thermal life. These are all examples of things we do in support of the design process. I also wanted to highlight an example of things we might do in response to issues we encounter in the field. This is a combustor liner from a CFM56 engine. So this is an engine line that's been around for a number of years. But we're still learning and improving the engine based on what we see in the field. So if you look at this is a part that's been subjected to very high temperatures. And if you look at this part, you'll see it's different colorations. The darker color, more oxidation. This is where a part has been exposed to higher temperatures. And the lighter colors are where a cooling flow has come in and cooled the part down. Those holes you see are part of the cooling scheme. And so downstream of the holes, you see the lighter colors. And so we can analyze this. So the upper holes, we do some single hole type analyses, very sophisticated large eddy simulations, trying to understand the effectiveness of the cooling scheme. And on this lower row, where the holes are more closely packed, we'll analyze the configuration more holistically with multiple holes in the analysis, and we can ask questions about how well they interact. And these are examples which were run up at Argonne National Lab. Part of what we're trying to understand is why do we see variations in the cooling pattern as you go around the part. And you can see this in terms of non-uniformities in the dark, lighter colors. And we can understand sensitivities of the cooling flow and of the larger flow to variations in the fuel, the variations in the manufacturing of the part, and the like. And the goal of all this is to ensure that we can, with confidence, deliver parts which can meet the required lifespan. And then just to remind folks that the same technology gets used outside of jet engines. Just a couple of pictures of wind turbines. Just talking to the far right for a moment, this is a single passage wind turbine with a LES calculation. Here we're worried about the operating range of the part, as well as the noise being generated by the wind turbine. If you haven't been near a wind turbine, you may not appreciate that they do have a bit of a distinctive noise pattern. And while they're not as noisy as jet engines, they do have some noise, and it does generate some amount of regs and community impact. And so we want to make sure they're as quiet as possible, while also being as efficient as possible. So these are detailed LES calculations that can help achieve that design mission. And then at the second from the right, is a sample of how we will analyze wind turbines interacting with one another. If you go back just a few years, wind turbines were only designed thinking about the isolated wind turbine. But the reality is they're often deployed as part of large farms, and the wake of one wind turbine will impact performance of downstream wind turbines. So increasingly we're analyzing that and designing for that as we lay out our wind turbines, but also as we lay out and design the wind farms. So let me sort of switch gears a little bit and talk a bit more about the software aspect of this and how that software has to respond to the changes of high-performance computing hardware. So I suspect most people on this phone call are aware that supercomputers have been advancing quite rapidly. You see different numbers thrown out, but one way to look at this is roughly a factor of 20 every 5 years. Alternatively, you can say it's a factor of 1,000 every decade. Either way, it's a significant improvement in the computational horsepower of our supercomputers, and this trend's been going on for some time. If I just look very briefly at computers that we've seen over the last, I guess, 30 some odd years, they're nearly back to the beginning of CFD at GE. They've changed quite a lot. In the 80s, with some of the we worried about vectorization. We optimized codes around solid-state disks. In the 90s, we were optimizing, thinking about reduced instruction set computing. As we get into the 90s and into the early 2000s, we're talking about parallelization, although parallel here is now talking about a small number of cores. And then as we go out into the current time, going much more parallel, tens if not hundreds of thousands of cores. And oh, by the way, that way that parallelism gets expressed is changing radically. So the computers have not been standing still, and that's an important backdrop as we think forward into the future. I told you earlier that we use a variety of software packages. A key one for us is a code called TACOMA, which is our in-house turbomachinery CFD solver. This is the code we use to design compressors and turbines, fan blades, steam turbine blades, pretty much anything in the engine other than the combustor. This is a code which we've been investing in for 20 years now, and this is where I'm actively involved. It's a large development team, and I won't tell you how many lines of code, but a non-trivial amount of modern Fortran code. And I'm highlighting in that middle block of bullets that we have a lot of features in the code which provide physics and fidelity to our designers, whether it's a variety of turbulence models, the ability to run steady and unsteady analyses, single blade row as well as multi-stage analyses, even advanced hybrid LES type capability, a fairly wide spectrum of computational grids we can absorb and run on. These are all the sort of features which provide fidelity to our design teams. And if you go back to where I started, our designers are needing to field these very advanced machines. That's been pushing us to ensure they have the ability to deliver, to analyze with high fidelity to deliver these advanced jet engines. And at the bottom there, I highlight that in addition to all this, we have to worry about the high performance computing, which increasingly means ensuring good parallelization. So MPI, OpenMP, OpenACC. And if I just can be entitled to brag for a moment, as somebody who's been involved in this code for a long time, this is deeply penetrated into the GE design system. And when I started way back when, I mentioned that we were talking about the return on investment of parts of high performance computing and equated the whole thing to the importance of electricity to modern civilization. It was actually in this context that we were having that dialogue about what is the value of a code like this. It's a key enabler to our design process. It's fully embedded. Something like the conservative estimate, more than 1 billion CPU hours over the last 20 years, and I'm probably low by an order of magnitude in that back at the envelope. But the story I want to tell here is about the way this intersects back with high performance computing. And so if I look at that 20-year history and try to articulate, in the early days the code was serial, and we were just worried about how to get good performance out of reduced instruction set computers, which back in that time period meant packing as many instructions as you could inside every loop iteration so that we could do the pipelining efficiently. And then to get into the 2000s, we went to the solve phase of the code, and we had to parallelize that. And back in that time period, as hard as it is to believe, we didn't know whether PVM or NPI was the right horse, since we had to abstract that. And then we get to 2005, and the solve phase is made parallel, but we're running out of memory in the setup phase. And so now you have to make the setup phase parallel. And I'm willing to admit here that we actually did it wrong the first time around. And I just mentioned this because, you know, this is not always easy to chase after what the computers require. But we did it right eventually. We got the setup phase parallelized. We got maybe a year of a breather, and then we had to realize that in the first pass at parallelization, we were focusing on running 8 cores. All of a sudden now, we get to 2008, when we're going up to national labs, we care about tens of thousands of cores, and that stresses the system differently. So you start, you know, performance tuning and trying to get the NPI commands more efficient and all of that. You get that done, and oh, by the way, the parallelization is being expressed different and finer grained, so we start worrying about going hybrid MPI and OpenNP as a way to go after strong scaling. You barely get that done, and all of a sudden last year we're worried about how do we get on the GPUs, partnering in this case with Cray and Oak Ridge. And we get that to a certain point, and now we're chasing after vectorization, interacting closely with Intel. So my point here is that you're constantly revisiting the HPC performance because it matters, and it matters because we still care about speed to deliver the fidelity that our designers need to do. And we still care about the HPC because the HPC architectures keep evolving on us, and we have to ensure that we can run efficiently on what we are able to buy in a given year. And I'd say here in the takeaway that although I actually have a lot of fun and enjoy the intellectual challenge of making the codes work well on computers, in all honesty, it's distracting from the core mission of ensuring our designers have the fidelity they need to deliver state-of-the-art jet engines. And I just wanted to highlight a little bit of that comments here. If you just zoom in on the top of 500 list, what I want you to see here is taking that story and putting it into timelines, that each of those stories are actually getting a little shorter as we go forward in time. And the point being that the pace of our software response to HPC, maybe I should say the pace has shortened, and the timelines have shortened, and the pace of having to constantly respond to something is increasing. And that's a bit worrisome as I look into my crystal ball. Having said that, though, that time and effort is worthwhile. Showing here on the left an example of scaling on the IBM Blue Gene Q. Note here, we're running up to 130,000 threads on the IBM, so very large scale calculations with very good performance, all because of that investment we've made. And then on the far right, just a demonstration that we can get speed ups at Oak Ridge National Labs using the GPU. So that time and investment does deliver the kind of performance and turnaround times that we need, but obviously it comes at some level of effort. And so this is really my last slide before I wrap. If you look at supercomputers, we're at a critical junction as we look forward. And I'm sure many folks in this phone are actually part of making the things I'm talking about on the slide a reality and can probably articulate the story even better than I can. But if I look in a very broad brush way at what we have today, there are two broad classes of architectures: multi-core machines, Linux clusters, the CPU-only Crays, the IBM Blue Gene Q. And then we have accelerator-based machines. Whether these accelerators might be GPUs or things like the Intel C. And a number of the big supercomputers in the top 10 list are also in this class. And so since we use computers from a variety of sources, we actively have to ensure good performance on these two different choices. And then if you look forward, there seems to be three things going on. Some of these multi-core machines will not be disappearing, but the leadership class computers seem to be evolving towards mini-core machines, so Intel fee-based, such as will be installed as for the next Argonne machine, or CPU GPU machines, where the GPU is even more important to the total flop rate, such as will be installed at Titan. And I look at this and I say, well, okay, so that's the hardware, and I presume that's what we'll have to be buying in the coming years. If you look at the software, then we have to have a programming model that supports this, and the part that's both intellectually challenging, but also a little bit worrisome, is that it's getting harder, not simpler. And so it's the MPI, OpenMP, OpenACC, throw in vectorization, throw in a task scheduler, and the need to be able to be somewhat agnostic about multiple hardware bets and architectures. And in parallel to this, the memory hierarchies are getting more challenging. And there are some glimmers of hope, of course, things like OpenMP 4.0 and things like the NVLink technology. But yeah, the hardware, my point here is that it's important to evolve your software for the hardware, and the reality is it's actually getting a little bit harder, not simpler, as we've gone through the last couple of years. So something which we have to keep investing in. So let me just wrap this up, and I think I've left time for at least a couple of questions. I want you to appreciate that that our business is under a lot of competition and a lot of pressure to deliver better products. It comes right from what the airlines are feeling in terms of their market pressures and the reality of fuel prices. That need to field better products is enabled by modeling and simulation and high-performance computing. And we're finding we need to do more sophisticated modeling and simulation, and so the high-performance computing size of computers and whatnot are growing, and our demands on that is growing. I've talked through the different aspects of an investment strategy to make this happen in terms of hardware and software, the validation, the ground you, and various types of organizations and people skills that are required. And I've kind of closed with a caution that the hardware and then the software response is at a key junction in technology, which we're having to manage very actively. So with that, Wilf, I'll hand it back over to you in terms of managing Q&A.
Thank you, Brian, for that really interesting talk. I'd like to encourage attendees to click on their Q&A button, open the Q&A window, and ask a few questions. Brian, I think you should be able to see some of those questions. Maybe you could pick a couple that are of interest to answer and answer them for the group here. I think there are several really interesting questions out there.
Sure, yeah. I just clicked over so I could see that tool. So the first question I see here is around vectorization, and the comment is that I showed in the slide as being something, it's a relatively new technology that we're looking at in very recent times, and the questioner was noting it's actually very old technology, and in fact, correct. If you go back to into the 90s when I was working out of NASA Ames, the vectorization on the Cray XMP and YMP was very important. And there are definitely some overlaps and similarities between that technology, but there was a long gap in between where that was not particularly important. And so to some extent, we are relearning and dusting off old books to figure out how to do it again. So it's sort of old but new all at the same time. And part of the challenges we're finding is that the compilers are having to get back up to speed to have the right support for that, and as well as we're relearning how to write code that make the compilers work effectively in it. So those are some of the challenges we're facing as we do that. Let me just read through the next question. And so another question here about how I mentioned TACOMA is written in modern Fortran. If I followed the question right, the questioner is wondering about the role of C or modern C in all of this. So that's actually a very interesting question. And I find the question between Fortran and C is borderline a religious war at times. I've actually written CFD codes in both C and Fortran, and I've gone back and forth a couple of times over, I guess I've been doing CFD now for nearly 30 years. I would still say if I had to write from scratch, I would be highly biased to write a code in modern Fortran. By modern Fortran, I mean Fortran 2008, with its abilities to encapsulate data, to write object-oriented methods. I think the compiler support tends to be better. I also think, and maybe this is just not being a programmer by trade, but being an engineer by trade, that C gives me more chances to get in trouble, whereas Fortran contains me a little bit better. I find it's a safer language to work with, especially when you have a team of folks who aren't programmers by basic training. So I still like Fortran in general, but like I said, I go back and forth between the different languages for different applications. So C definitely has a role in high-performance computing.
I think we have time for one more, Brian. Do you want to pick one more, and then we'll wrap it up?
Sure. Yeah, just kind of trying to read through questions here real quick. Yeah, so there's a couple questions here about universities and how GE works with those, or to what extent we work with universities. GE has an extensive relationship with a number of universities for a whole variety of our design challenges. So for aerodynamic concepts, as well as demonstrating aspects of high-performance computing. I showed an example of a large eddy simulation run at the University of Southampton as part of a GE-funded project. And so it's part of our story. And so, yeah, we do use universities. GE is a little bit different than a company such as Rolls-Royce in that we have a strong research center. So part of what some companies would use universities for, we use an in-house corporate research lab for. But we do make use of university partners quite extensively throughout our development process.
Well, thank you, Brian. We're going to, a couple of things just to sort of wrap up with. We've got a fairly good list of really interesting questions here, and we'll try to answer them all on the web. We also will be posting the streaming media for people to view later, and we should be getting the information on that out in the next couple of days. So Brian, thank you so much for this presentation. It's been extremely interesting, and the questions we're getting are indicating that a lot of people have found it that way. So thank you very much indeed for taking the time to present to us today. Thank you.
You're very welcome. It's been my pleasure.
Thank you.